Well, I will continue on the same theme we started earlier today about sellers trying to sell a good. And as in the previous talk, there is one seller who faces again one buyer and has one good. But we're going to be in the space of situations where the seller has private information. And if you think about, experience, sellers often do know something about their goods that consumers do not know. And we have a classic result. Arkelov's insight said that, well, if consumers don't know something about the quality of the good, it is the average quality of the good that's going to be driving the market price, and then high quality goods are not going to be traded, so we're going to have some type of market inefficiency. On the other, there's another classical result in economics, which was, I think, first stated by Viscousi in '78. They said, well, if certification costs are low, so if the seller can easily get a certificate about the quality of the good, then it is the high quality who is driving the market forces, because that high quality has the highest incentive to obtain the certificate, and then information unravels. So yesterday we looked at an informed seller who, in contrast to the Arkelov's seller, could do any selling procedure to sell his good, and we saw that there are many things he could achieve, including achieve ex-ante optimal profits, the profits that he could achieve using the best mechanism that he could choose before knowing his information. The result we mentioned yesterday included situations where the seller's information was about a pure vertical dimension. Today, we're going to revisit this question, but we are going to allow the seller to have certifiable information, evidence. So I've been very lucky here to have had two excellent lectures on mechanism design with evidence, one by Eddie and one by El Halal. I hope I'm pronouncing the name correctly. And so we are going to be in that situation where there is evidence, which is exogenous, but the seller can choose any selling procedure. But to put everybody kind of the same page, I'm going to start with an example, and we're going to together analyze it based on what we learned yesterday about the soft information case, and then move on to talk about certifiability.
Can you record what is the soft information?
Soft information is the case that we are looking most of the time where one type can mimic each other without any problem. Soft information is the case where one seller type can mimic us and one consumer type can mimic each other. So when Sergio was writing down incentive constraints, one type could mimic the other or could choose the menu of the other. When you have, that's the case of soft information, to contrast it with the case of hard information where you have pieces of evidence.
To prove my type.
Yes, so I have a piece of paper that says my type belongs in this set. So I'm going to introduce all of this terminology once I enter the space of slides. But let's first start with a simple example, which, as I said, there's going to be one buyer, one seller. The seller's type is going to be either S1 or S2, equally likely. And the consumer type is going to be T1 or T2. Again, equally likely. So in this matrix, I'm going to denote the buyer's valuation for the good as a function of the seller's type and his type. So this is 5, this is 3, this is 1, and this is 2. So let's think about this situation. So think about S1 as being the high quality wine, or the high quality any good, and S2 low quality. T1 is a consumer that values S1 at 5 and S2 at 1, and T2 is a consumer that values S1 at 3 and S2 at 2. So T1 is a consumer that is more sensitive to quality than T2. So I am T2, I can tell which one is better, but I'm not a big connoisseur. Maybe some of you are. So T1 can really prefer 5, really prefers S1 to S2. Okay, so let's start easily. Suppose the consumer knows whether the seller's type is S1 or S2. So what we know is that what is the best that the seller can do if the consumer knows that his type is S1? the best he can do is to ask a price, right? That's what we've been seeing all today.
Can you, if the
So now, when the consumer knows that the seller's type is S1, we are in the situation that we were discussing earlier today, but actually in the simple case, because now the private information is it's single dimensional. You are either T1 or you are either T2. So now, when the consumer knows that the seller is S1, the best that a S1 seller can do is to ask a price of 3, right? And both consumer types will accept the price of 3. Excuse me?
You're assuming half our probabilities.
Yes, I also said equally likely. I said everything is equally likely. Yes, everything. I said everything is equally likely, but let me just write it down. Yes.
And also independent. So
And independence, absolutely.
For each cell.
Everything is independent, thank you, and equally likely. I said the word equally likely, I didn't say the word independent. Everything is independent and equally likely. So if the consumer knows that you are S1, the best you can do as an S1, you can ask a price of 3, the consumer will accept. So I will call VS1 of full information. The profit of S1 when the consumer knows his type, the best he can achieve is 3, and V of S2. Now, if the consumer knows that you are S2, you are indifferent between asking a price of 1 and always be accepted, or a price of 2 and be accepted with probability of half. Your profit is going to be 1. So this is a vector of profits 3, 1. This is the best the seller could have achieved as a function of his type if the consumer knows his type. Now, another thing that the seller can do, given that the consumer does not know his type, is ask a price, let's say, of 2. If the consumer doesn't know whether you are S1 or S2, would he accept the price of 2? Let's think about this. Well, the expected value of T2 is 2.5, because he values the good a half probability 3, a half 2 is equal to 2.5. Yes? So his expected value is 2.5. This expected value is 3. So a price of 2 is always going to be accepted, and that's good. That's another way to sell the good, but of course you can always ask a price of 2.5. That's better. And the price of 2.5 is also going to be accepted. So when you ask a price of 2.5, both seller types will make I will call this EO for ex ante optimal, because I'm going to explain that there is nothing better the seller can do from the ex ante perspective. So the profit vector at this posted price is 2.5, 2.5. Yes?
You're writing the buyer's payoff.
The sellers. V of S1 is this. I'm using now V because this is the notation is used in many of these papers. The interim payoff. So V is the
seller's profit.
Is the seller's profit.
So previously it was.
Previously
it was probably one which is okay. Sorry, you're right. Yeah. Okay.
It's 2.5, 2.5. Because now we're both now we're asking price of 2.5, and because the consumer doesn't know if you are S1 or S2, he will accept that price. So, yeah, what we did yesterday, we wanted to investigate what would be selling procedures that are going to be equilibrium of the game, where the seller is choosing any selling procedure at the interim stage, knowing S1 and S2. And we said that any equilibrium profit procedure is going to result to an equilibrium vector of profits. And this equilibrium vector of profits, in order to be what we call equilibrium, it must be feasible in the sense of being incentive compatible and satisfy voluntary participation constraints both for the seller and for the buyer. And I'm going to repeat the same things today later, but I'm just revising what I said last time. So first it has to be feasible. And second, this vector of profit has to be immune to any deviation. So no matter what mechanism the seller deviates to, I can find some belief that equilibrium play of that game, given that belief, will result to a vector of profits that is not that is less or equal to for each seller type compared to what I'm conjecturing to be an equilibrium vector of profits. So the first observation we said is that in an environment where the seller cares only about revenue, feasibility will imply that both seller types must have the same profit. So feasible vector of profits must be on the 45-degree line. So if I plot, if this is here the interim profit of seller 1, interim of seller type S1, interim because we're taking expectation with respect to the consumer types, and if this is the interim profit of seller 2, then anything I can expect to be on the equilibrium is on this 45-degree line.
Does it depend on the fact that the publicities are the same?
No.
Because if it is 1, then it is 3. Oh, okay.
No, because you can still mimic each other. Even if the probability is epsilon that the type is S1, S2, you can still mimic him.
But if the probability is 0, then it's different.
Yes, that's true. So here, let's put these two. Oh, no, actually, no, I don't want to put this here. Let's suppose this is 2.5. 2.5. All right. So this price of 2.5 is important because actually it yields the seller the highest possible ex ante profit. So if the seller was able to choose the best selling procedure before he knows whether he's S1 and S2, he cannot do any better. Why? He's extracting all the surplus from T2 with this 2.5, and if he tries to extract a little bit more from T1, T1 will try to mimic T2. So of course that is not a proof, but that's like you can see it almost easily that you cannot do better than 2.5. I know that this is all trivial, but bear with me. I'm going to get into the more interesting things. So 2.5 is an ex ante optimal mechanism, and what did we do last time? We showed that actually the game where the seller is choosing a mechanism at the interim stage and the seller's information is solved has a continuum of equilibrium outcomes which are between this point 1, 1 and 2.5, 2.5. So all of these things are equilibrium outcomes. And how can you support the vector 1, 1 as an equilibrium profit vector? Well, you can support it because no matter what mechanism the seller deviates to, I can always be convinced that the deviation is coming from S2. And if I know the most money I can extract from S2 is 1. So otherwise, if I could extract more with that mechanism, then this is not Meyerson's mechanism. We know we cannot extract more from S2 than 1. So then S1 has to have the same interim profit, otherwise we would have no feasibility. So we can support any vector between 1, 1 and 2.5, 2.5 as an equilibrium outcome. All right, so you see though that the full information vector, profit vector, was not even equilibrium candidate because it was not feasible, right? In that case, S2 would want to mimic S1 because S1 gets 3. So that's what we basically did last time. What we're going to allow today is for Mr. S1 to have a piece of paper to say I'm S1, or if S1 is selling wine, to be able to give a glass of wine to the consumer and say, try my wine. So now S1 can prove that he's S1. So obviously, if S1 can prove that he's S1, this price is not an equilibrium outcome because S1 says, wait a second, I am S1 and the price is 3. So potentially this is the equilibrium could be an equilibrium outcome because now this is not anymore, and you see that this is worse from the ex ante perspective. Because if I take the ex ante profit corresponding to the full information vector, profit vector, the ex ante profit of this one, so let's call it, I don't know, V bar, is a half times 3 plus a half times 1, it's 2. So, all right, so let's look. So now let's suppose the seller has this ability to certify, to show that he's S1, which means that S2 cannot mimic. So now S1 can make 3. So what do we know about this situation when the seller can only ask prices? If the seller can only provide evidence and ask price, so what is the selling protocol? I can provide any piece of evidence I want and ask a price conditional on the evidence. Then the unique equilibrium outcome of this game is 3-1. Why is that? Suppose there was an equilibrium where both seller types were quoting a common price with positive probability. So in that case, the consumer doesn't know if it's S1 or S2 because it's a pooling price. So then, if both consumer types are accepting that pooling price, in particular if T2 and T1 are accepting it, it must be below 2.5. But then cannot be in equilibrium because S1 is saying, wait a second, I am S1 and I want 3. He will make more. Now suppose that pooling price was accepted only by T1. That pooling price cannot be above 3 because the expected payoff of T1 is 3. So then S1 can say, oh, wait a second, I'm S1 and the price is 5. So again, he deviates. So this argument has been used to establish that in these situations where the matrix is pairwise monotonic, it was established by Frederick Koestler and Resistor, and no, the unique equilibrium outcome is unraveling. So 3-1. So we know that with certifiable information and posted prices, we're going to be here. So now let's think about more general selling procedures. So I'm going to talk about another selling procedure that is not a posted price, but it's not a very difficult selling procedure either. And I'm going to describe it first and then write the allocation it results afterwards. So the seller goes to the buyer and tells him, look, if I give you a good wine to drink, or if I show you the certificate that my wine is good, the price is going to be 3. Otherwise, it's going to be 2. Do you want this? Do you want this contract? So you're going to be facing a price of 3 when the evidence is good and a price of 2 otherwise. So suppose you accept this contract. So what is going to be the allocation as a function of types? That's called an evidence, we call this an evidence conditional price. Just a second. All right, so the person, you are offered this contract. Do you want to accept it, yes or no? What is your expected payment? Because you don't know who is offering this. In expectation, you're paying 2.5, right? So the consumer will accept it. And this, it's feasible because now seller S1 is getting 3, but S2 cannot mimic S1 because S2 doesn't have the evidence S1 has. And T1 and T2, they can either accept or reject. There's nothing to do. Whatever you report, you get the same deal here. So that's feasible. And it yields a profit vector, which is somewhere here, 3-2. This profit vector is ex ante optimal. Why? Because ex ante profit, what is the expected profit of 3-2, the vector? With probability 1/2, the seller is going to get 3, and with probability 1/2, the seller is going to get 2. This is 2.5. Yes, so it's ex ante optimal. I hope that's easy to I don't, everybody's, it's after lunch, everybody's so quiet. I'm getting very nervous. Either
It's a sign of your clarity.
Either everything is thinking this is completely boring or completely trivial, or I'm completely lost with these 3s and these 2s. Okay, so so this 3-2 is another way to do ex ante optimal, to do an ex ante optimal mechanism. All right, so now
So before, so
Yes, but the protocol was I will present evidence and ask a price. Now, so the timing was I will tell you an evidence and ask a price. Now the seller offers you an evidence conditional price. So it says, if my evidence is this, that's going to be the price. Otherwise, that's going to be the price. It's an evidence conditional price. It's a contract that is conditional on future evidence. So, you know, they hire you as an assistant professor, and if the evidence comes out to be good, you get tenure. If not, so that's not a good example to say to make people nervous, but maybe, you know, and it doesn't really match this, but it has this flavor that if things turn out to be good, this happens, and if they turn out to be not so good, you face another thing.
So before, the seller was giving evidence for free, and in this example, the seller is actually charging something for the evidence. He doesn't give the evidence for free. He will only give the evidence if the buyer agrees to pay.
He only... Yes, the evidence is given after the mechanism is accepted. That's very correct. So first the mechanism is proposed, and then the evidence is provided.
So is that why the price is higher? Because
That's the way you can do better. We're going to actually show you that that's a canonical way to think about certification in the general mechanism design problem when you have an informed seller. I'm going to explain this. But before we go any further, let's do something again easy. Let's try to think about all the ex-ante optimal mechanisms here, all the ex-ante optimal profit vectors. There's a continuum of them, starting with this one, which is the 0, 5, and this one, which I hope this is looks like a straight line, and this is like 5, 0. So why are all these ex-ante optimal? Because any point on this will, if you take, has an expectation of 2.5. So here you have one ex-ante optimal profit vector being in equilibrium with soft information. Here we have this other profit vector 3, 1, 3, 2. Here we have this unraveling. So this is what Frederica and I were thinking. We thought, okay, we have interdependent values. We have certifiable information. We know from the case of soft information we had a whole continuum of outcomes. We know this is a unique equilibrium with posted prices, so we really thought that this thing is going to be in the set of equilibria. 3, 1, this unraveling, because this is the unique outcome with posted prices. So sadly for us, it's not an equilibrium. And actually when you have certifiable information, what we're going to see today is that the unique equilibrium outcome is this 3, 2. Unique. And what was mysterious, because I will show you how we know that this is unique during the talk. What was completely mysterious to me was why this freaking 4, 1 is not an equilibrium. I was like, thinking, what's the difference between 3, 2 and 4, 1? 4, 1 gives at least 3 and 1. So we need that this is an S. Let's think about it like logically. Here we have certifiable information. Every seller type must make the same, at least as much profit as they make when the buyer knows their information. So because here once as one seller as one can prove himself, then of course S2 is known. So we know that S1 must make at least 3 and S2 must make at least 1. And 3, 2 has this property, 4, 1 has this property. They're both ex-ante optimal. It turns out only this one is an equilibrium. So now that I'm going to move to the slides, I am going to, and the analysis is going to show you why this is an equilibrium, how to find this equilibrium in general, and explain the difference between 3, 2 and 4, 1. So this lecture is on this paper with Frederick Kessler, Selling with Evidence, that you can find. Oh, What did you do to this?
I didn't use it. Maybe it's not connected.
Yes. Oops. Yes. That's like a necessary condition. Okay, let's put that. All right. Okay. So we know that. So let's think a little bit more about what we mean with what means to have evidence. So the case of soft information is basically it's a special case of having evidence, but the evidence that each type has is that I'm either S1 or S2. That doesn't say anything new. So because we already know that the seller's type is either S1 or S2. So when each player basically can prove that they're either S1 or S2, thank you very much, we cannot do much. We don't learn anything. But what we know is that we can actually write down the set of types that S1 can mimic. He can mimic himself and he can mimic the other type. And the same thing for S2. So for every certifiability structure that satisfies what El-Halan and Eddy was calling normality, so it's closed, you can send many messages, you can send intersections of messages, we can write down this set, which is basically what you can call this a set of types you can mimic. So with soft information, you can mimic everybody. Another possibility now is what I was mentioning earlier, is that S1 has a piece of paper that says I am S1. So now S1 can mimic S2, but S2 cannot mimic S1. So in most of the talk, we will actually be looking at the case where any seller type has a piece of paper that says I am S. That's the case of own type certifiability. And the reason we're looking at this case is because the main result we have it for this case, and also because it's kind of the polar opposite of the case of soft information. It's a case basically of very small certification costs. So now, what does certifiability do? When you think about it, I already told you that we're going to get one equilibrium outcome in this example where we are getting a continuum with soft information. A priori was not obvious to us because certifiability, the first thing it does, it makes the set of feasible allocations bigger. Why is that? I have to worry about less constraints, less incentive constraints for the seller. Now some seller types cannot mimic each other. S2 in that example could not mimic S1. So that is good because I get a bigger set of feasible things. So an equilibrium thing must be feasible and immune to deviation. So the first thing goes in favor of enlarging the set of equilibria because I get more feasible outcomes, but I get more compelling deviations. So now when the seller is deviating, he can actually prove who he is. And deviations now, I also get a lot more feasible deviation payoffs. And it turns out that this interaction makes the equilibrium set smaller, and if you're willing to buy some assumptions that I'm going to tell you at the end, generically unique, but I'm not going to insist so much on this uniqueness. I will explain why. But what I want, in the case, as I said, of own type certifiability, where every seller type can prove himself, we know that an equilibrium vector of profits must yield each seller type at least his full information profit, so his Meyerson profit. So I already explained all this, so I don't want to talk about this now because I told you that all of this, I talked about this. So that's basically where we are. So let me remind the model. It's the same as yesterday for those who were here, but those who were not here, now you have a chance to understand. Excuse me? Now you have, for those who were not here yesterday, you can actually see the model and we can be precise about what we're looking at. So the seller has privately known type S, which belongs in some finite set. The consumer has a privately known taste T, and it's uncertifiable. What is different here now is that S is certifiable. I want to mention that the result I just told you yesterday could hold for multidimensional types here, because of course it's very difficult to find what is this ex-ante optimal thing, but once you have it, nothing hinges here on nothing hinges in the arguments on the dimensionality of types. That's an aside. All right, so now types are independent. The prior mu naught for the seller's type, everything is finite. I'm going to work with finite type spaces. The prior on the consumer taste is tau. The buyer's valuation is a real value function. The seller's reservation value is a real value function. For this case of certifiable information, I am not going to restrict attention to sellers that care about revenue. So here we are going to prove a theorem that holds for arbitrary cost functions and arbitrary valuation functions. No assumptions on monotonicity or single crossing, just real value functions. So an outcome of this game, which I haven't written down, but I'm going to tell you the game in 1 second, is going to be a probability of trade and a transfer. And now, of course, when I showed this to somebody, they told me, you are crazy, you're using this notation, and I understand Sergiu's pain. This is I'm following their notation in Roger Myerson's paper, who calls the probability P and the payment X. And there are many people who think that I'm crazy that I'm doing this. Maybe P for price and Q for natural, but in any case, that's how we wrote the paper now. So P is the probability of trade and X is the transfer. So an allocation will specify for each vector of types ST a probability of trade and a transfer. And the players are risk neutral, so the seller's profit when the types are S and T is the transfer minus the probability he gets the good times his reservation value, and the buyer's utility is the probability he gets the good times his utility minus the transfer. And as I was mentioning yesterday, this is the important piece, the interim profit vector for the seller. So when we take expectation with respect to the consumer's type, and when I'm thinking about the interim utility of the consumer, of the buyer, it's important to understand that sometimes the beliefs of the buyer will be changing. So I'm writing this an index with a belief mu, because this mu at certain points in the game might not be the prior anymore. So that's the same as last time. Here we will also need to make some assumption on the transfers. They belong in a compact and convex set. So this X can be arbitrarily large, and we are using this to prove existence. Otherwise, we have a problem of existence. This is done this is done also in other papers in the literature who try to prove existence. So this is not very substantial. You can think of this calligraphic X as being arbitrarily large, but we need the boundedness. So as yesterday, the seller and the buyer can communicate via chip talk messages, and the seller can also certify. So the set of certifiable events is a set of subset of all subset of a seller's type, and we assume that is closed under intersection. This is the assumption of normality that was presented early in the summer school. And this is exogenous. So each seller type S has a set of events that he can certify, and we assume that this is non-empty. So when the certifiability structure is closed under intersection, we can write down this R of S, which is the set of types that you can mimic. This corresponds. These are the set of types that you can mimic, and basically, the difference between this and the standard framework of mechanism design where information is soft is that when we write down the incentive compatibility constraint for the seller, instead of having saying that the seller cannot claim to be any S, now he cannot claim to be any S only in R of S, because these are only the set of types that he can mimic. That's the difference. So the certifiability structure satisfies own type certifiability if the singleton S is in the evidence structure, which implies that the set of types that each type can mimic is just himself. So that's an example. So when you have S1 or S2, then you cannot mimic anybody. So in that case, basically, the incentive constraints of the seller are completely trivial. We don't have to worry about the seller. The seller, whatever mechanism we propose, we are going to ask the seller to offer this maximal evidence he can, and we don't have to worry about the incentive constraints. It trivializes the problem in this way. But as I said, it doesn't make the problem of mechanism selection easier necessarily, because the way it makes the incentive constraints easy to satisfy on path, it can also do the same off path.
S in E does not imply that other S are not in.
Excuse me? Yes, of course. But that's a very good point. Yes, but the revelation principle for games of certifiable information says that without loss of generality, under normality, we can restrict attention to mechanisms where the seller, each type of the person who has certifiable information is obligated to provide the maximal evidence, and under this maximal evidence, these R of S, the set of types you can mimic are those who can provide the same maximal evidence. This is the essence of that revelation principle result, and that's why it's important that you have the you can also provide the intersection of messages, that you can each one can provide the intersection of messages, because that's what Eddie Deckel was saying. You can either prove that you can sing or dance. If you can do both, you have to be able to show the piece of paper, I can sing and I can dance. And under that condition, types who can sing and dance can only mimic each other. If you remember that analogy that Eddie was saying. All right, so let's talk about the mechanism proposal game. So now we're thinking about equilibria of this game, where first the types are drawn and the seller will propose any procedure to sell the good knowing his type. And the procedure is going to be a mapping from the evidence structure, which is exogenous in this model, exogenous. And a set of messages that it's specified by what is he choosing, and a set of messages for the buyer. And this mechanism is going to map evidence, messages from the seller, which are soft messages, messages from the buyer, to a probability of trade and a transfer. Obviously, under own type certifiability, we don't really need to think about the messages of the seller, but we have some results for partial certifiability, so I'm writing down the general definition. Are we fine? So now, the first bullet point, yes.
Can we split that? If the type of the seller can prove himself,
Yes.
are you saying that you can restrict attention to the case where he does that?
We could write it like that. We don't.
It's clear enough.
Well, good.
But here,
It's
no.
easy.
Come on, you know that. No. But the difference here is that the evidence is with the principal, not the agent.
Yes, I know. Let me.
So
That
it's not clear to me why. I mean,
we don't use it.
The seller might not want to review the next one. I mean, maybe under the assumption of preferences that happens, but in general, it's not clear to me that you would want.
I will explain.
Okay. We'll explain later.
In 1 second. Let me write.
No, the argument of agreeing upon these local arguments, you can replace for each one, for each level transitivity condition, you can apply the relation principle. You don't have to do it globally. So it doesn't matter that you have in addition other people for which you don't apply the relation principle. It's a trivial argument.
Offering the mechanism, it's not the same setup.
Let me finish. Let me finish the description, and I trust that maybe you see things that I don't see, but let me try to finish, and then we can discuss. So let me.
It's a valid question, but I think there is a good answer to it.
So it's actually it's a bit subtle, because I understand. So basically, here there is a subtlety which I want to explain after I took about the timing. Okay, so we are proposing this mechanism. The evidence is presented in the mechanism. So if you don't like to think about the seller just presenting evidence and and not cheap. We don't in the paper we allow an arbitrary messages for the seller as well, but the evidence is presented in the mechanism. Okay, and I will explain that in 1 second. So this is the mechanism. That's what the seller proposes in this game we're playing, and these are finite things. Now, we assume that they observe a uniformly distributed public signal. This is just to convexify payoffs for existence. We need to use some fixed point, and we need public randomization. We need this kind of public randomization device to get some well-defined set of payoff vectors. It's not substantial, so just this is for technical purposes. But what happens is that the seller certifies an event and sends chooses a message among those who are available. The type decides whether to participate or not and sends a message. And this participation and reporting decisions could be random. So a seller presents some evidence and chooses as a function of his type a probability distribution over messages. The buyer decides whether or not to participate and chooses as a function of his type a probability distribution over reports. An allocation is implemented as a function of the mechanism and the reporting and participation strategies. So now there is a good question asked by El-Halan. Why do you have the evidence submitted in the mechanism? Another way we could do it is say, okay, as in the posted price timing, the seller first proposes evidence and then a mechanism. So it's without loss of generality, and we put it in to model it this way. Why? Suppose you had a situation where some seller type showed some pieces of evidence, so they kind of showed we belong in this set S, and this is the mechanism we propose. Now, you can achieve the same outcome as you doing the following. You propose a mechanism where the seller types who were basically pre-certifying themselves are getting exactly the same outcome as is in the original mechanism, and for all other seller types, the mechanism is supposed to pay the consumer some money. This mechanism is always going to be accepted by the consumer because the consumer can actually understand from this proposal that this must be coming only from those types who could certify this event E, because everybody else is paying him money for nothing. So in this situation where there are transfers, this is a canonical way to have the timing performed. In another situation where you had no transfers, that's with the loss of generality. If you had competing sellers, it's with loss of generality. Here it's without loss of generality to have the evidence presented in the mechanism. So first the seller proposes a mechanism which is going to specify as a function of the evidence and the chip messages a probability of trade and a transfer. But I think El-Halan was also asking something else. He was asking, why would you have like a revelation principle type of result here, right? Well,
more specifically, couldn't it be the case that the principal would prefer the agent not to know which type he is?
he will not know given the proposal. He will know nothing.
Well,
Because
remember, the certification is after the mechanism has been accepted. The agent doesn't know what the evidence is until after the mechanism is accepted.
so you are talking about my next slide. So let's talk about what is an equilibrium now of this game. So this is the same thing as I put on the slides yesterday.
Price that's contingent on acceptance.
So an allocation P and X is going to be okay. I think it's good to present.
Is the answer that Eric gave the right one?
Yes, yes.
Evidence is actually going to be shown after.
After. So the proposal is not going to reveal anything. Actually, and this is Here, this is encoded in this word prior. So an allocation is an expectational equilibrium, which is essentially equivalent. This is a notion, it's written in Myerson's 83 paper, which corresponds to strong perfect Bayesian equilibrium. If you're wondering what strong means, it means that different types of the buyer have the same beliefs about the seller. If we allow different types of buyer to hold different beliefs for deviations of the seller, we make our life easier. It's easier to kill deviations. Here, if you deviate, all types of the buyer will think the same way about S. And that doesn't make it life easier. It's just, and actually, it's actually how the solution cosm was written. Okay, so an allocation is an expectational equilibrium if it's feasible for the prior, which means, or where is the I should have put the feasibility. Feasibility means incentive, compatibility, and participation. And now there is an issue for which belief of the consumer is this feasible, because maybe the proposal reveals information to the buyer about the seller. And the scrutability principle of Myerson says without loss of generality, all principal types offer the same mechanism. Why? Because if we had an equilibrium outcome where some seller types were proposing mechanism A and some other seller types were proposing mechanism B, those proposals would reveal information to the consumer. So they had to be feasible only on average over the set of types of seller on A and over the set of types of B. But now if you have a mechanism which says, well, if the seller types belong in A, this mechanism will equal mechanism A, and if the seller types belong in B, this mechanism will equal the mechanism that the B types were proposing. This set of feasible, this will result to this mechanism will implement the original outcome. It will still be feasible. So without loss of generality, all seller types propose the same mechanism, which means for our purposes that if we're looking for equilibria, we're going to think about mechanisms that are feasible for the prior, and they're also immune to deviation. So a mechanism is immune to deviation if for every mechanism M tilde, I can find some belief that the buyer holds for the seller, mu tilde, and a reporting and participation strategies that form a continuation Nash equilibrium or base Nash equilibrium of that game, of that mechanism mu tilde, given that of path belief, that yield an outcome P tilde X tilde for which the interim profit vector for the seller V tilde is less or equal to V of S, which is the profit vector corresponding to what I'm supposing to be an equilibrium. This is already the same as yesterday. The only difference now is the type of game, because now we have the evidence. Any questions about that? So, as I mentioned yesterday, this is a summary of the definition. The proper definition requires a lot more space to describe, because I have to be more precise about what we mean by reporting and participation strategies. But I hope you kind of get a sense of what we mean.
The mu tilde here is arbitrary?
Yes. So basically, I am free to choose any belief I want of path to make something unattractive. But the problem is, still, it's not so easy to find a belief that works. It has to be tailored to the particular mechanism. And the proof we're going to do,
Out of equilibrium.
it's an out of equilibrium move.
With zero probability.
So you're seeing something that you're not expecting to see. All types are going to propose the same mechanism. So if you're expecting
There is one belief for which you kill it.
one belief,
For which it kills this deviation.
yes,
Right? Or I'm doing the negative.
Yeah.
that's the right. That's correct.
Some belief.
Mu tilde, mu tilde is
So
the
there's
belief
some
that-
belief this deviation is not worthwhile, but why? What does this belief come from? Okay.
It's arbitrary.
That's a perfect Bayesian equilibrium. Out of equilibrium, the beliefs are not pinned down
Okay.
by Bayes.
Okay. Okay.
Now you can ask me, is this a reasonable solution concept? That's a different discussion. This
Okay,
is
okay.
this is the solution.
We are not going there. It's okay. I just want
Thank you. Because that would be, we already have uniqueness, so then.
No, the quantifier, there are too many negations here. And that's-
Sorry.
So I was trying to fix.
I hope it's correct. I think it's correct.
No, it's okay. It's correct. Yeah.
Yeah. So here, now an allocation is feasible for some belief mu, if and only if the following incentive and participation constraints are satisfied. So why this is a result and not a definition? Because we have certifiable information. So the Bayesian incentive constraint and the participation constraint for the buyer are standard. The participation constraint for the seller is standard. The difference is the incentive constraint for the seller, which requires, which basically something is feasible if if S cannot benefit by mimicking another type S prime that among the set of types that he can mimic, which are basically the set of types that have the same maximal evidence. And this result, there are many versions of the revelation principle. Contemporaneous forces, François Force and Frederic have a version, Denneker and Severinov have another. Green and Lafon is the first paper.
Is R transitive in your model?
Excuse
Which
me?
means if S prime is in RS and S double prime is not S prime, does it imply that S double prime is in RS?
I think so, yes.
Because that's a Green-Lafon condition for which everything clearly follows. That's all
Well,
it
no,
needs.
Green Lafon need more.
That's all it's needed for that. For the positive result, which is a triviality then. It's just this transitivity, nothing else. All the rest is red herring.
Okay, all right, maybe in any case, so the R of S is the way this definition of R of S is how François and Frederic do it. There are many other citations. I could have had them. They were discussed extensively in the summer school. We have them in the paper. So this is the same. I'm citing this paper because that we are using this construction that they introduced. All right, so I'm going to give two definitions that I will actually describe in a hand-wavy way while I was talking through the example. An allocation is ex ante optimal for some beliefs pi. Sorry, it could be mu. I'm using mu most of the talk here. If it maximizes the ex ante profit vector, ex ante expected profit under interim and participation constraints. So an ex ante optimal thing is something that the seller could commit to choose before he knows his type, and that's the best he can achieve, obviously, among the feasible things. Of course, this also accounts for the fact that there would be informational constraints coming in the future. Then the other benchmark is what we call full information optimal for every S if it maximizes the interim profit V of X under the V of S under the following exposed incentive and participation constraints. So now you see I'm writing the incentives exposed, so as if the consumer knows S, which is exactly the constraints that we write down in the case where the buyer knows the seller's type, which is the most cases in Meyerson, Riley and Zeg, Hauser, and so forth. So where the S is known. Now, full information is obviously a bit of a confusing term because there's still asymmetric information about the consumer. So it's not complete information. It's full information just refers to what the buyer knows about the seller. There's still an asymmetric information about the buyer, as in the main paradigm. All right, so now we want to think about finding equilibria. So here, there's a lot of things that so let's be a little bit pessimistic, or not pessimistic. Let's think about, here we really don't know what can be an equilibrium when we are starting off. But let's think about the following exercise. In mechanism design, we start with a given prior, and we characterize all feasible mechanisms. So suppose we start with a prior, we characterize all feasible mechanisms, and then for each of that mechanism, for each feasible mechanism, there is an interim profit vector for the seller. Now I can look at the Pareto optimal profit vectors for the seller for that belief, and I can do the same exercise for all beliefs. So for all beliefs, I can think about everything that that is feasible, And then I can take the Pareto frontier of all the things that are feasible when I vary all mechanisms and all beliefs. I'm simplifying over a few things here, but bear with me for those who know the details. So let's take the Pareto frontier of all of these profit vectors, and I will call this strong Pareto optimal profit vectors. So these profit vectors are very compelling. They are basically on this Pareto frontier, so it's really hard to imagine what can kill them, what deviation can kill them, because I'm already pushing I'm taking every belief and I'm taking all mechanisms and I'm for a given belief and I'm taking the Pareto frontier profit vectors, and then I'm doing this for every belief and I'm taking the frontier of the frontiers basically. So if something is on the frontier, it's hard to get beaten because it's on the Pareto frontier. So basically if you may, but it's not obvious that this works. And I'm going to, so what we're going to show, which this idea of looking at these Pareto frontier vectors is in a beautiful paper that I was discussing yesterday by Eric Maskin and Jean Tirole. They develop this, they look at this strong, they call it strong and unconstrained Pareto optimal profit vectors. They use the word unconstrained because they ignore the in principles incentive constraints. Here we don't have principal incentive constraints when we have on-type certifiability, so we don't need the word unconstrained. And so what we're going to do, we're going to use this idea of looking at frontier profit vectors. We are going to show that they exist for all that a Pareto frontier profit vector exists for all priors. So no matter the prior, it has a good profit vector. And that's not clear. There are many games, many situations that are not part of the problem we're looking at where this property is not true. And then we're going to show that this is an expectational equilibrium outcome, and actually it's ex ante profit maximizing. So for every prior, the Pareto frontier profit vector is going to be ex ante profit maximizing and immune to deviations. And we're going to show that this is an equilibrium. So now I'm going to show a trivial example and actually I'm going to show you a way to prove that something is an equilibrium via a game theoretic argument. So the argument is going to rely on a zero-sum game min-max type of logic. This argument is relatively simple to use, but it doesn't work for all problems. But it's simpler to understand, so I'm going to start with this. And I'm going to look at the most fascinating example that has been looked in economics, where the seller has two equally likely types, S1 and S2. The valuation and the reservation value of the consumer is always 0. So we want to establish this fantastic observation that if both S1 and S2 give 0 to the buyer, the unique equilibrium profit vector is 0, 0. I hope you don't get embarrassed by the triviality. But at some point we thought that we couldn't prove this. So maybe that shows something about us or maybe about me. But I'm going to show you why we thought maybe there's no equilibrium in this game. We know that, from Arison's paper in 83, it's a very general problem, but it doesn't have certifiable information. So, it could have been in this case. All right, so now I want to show that 0, 0 is an equilibrium. So if it's an equilibrium, it must be immune to deviations to arbitrary games. Right? So one deviation I can think of is a game where you play left or right. Now the consumer has no type. His type is 0, 0. There's no type. The consumer gets 0 no matter what. So basically the payoff matrix we're looking at, just to be clear, is that you have two seller types, S1 and S2, and there's one type and it's 0, 0. That's it. So now the seller deviates and offers you to play this game where what's happening in the game? The seller will present his evidence. So now we have some own type certifiability. So the seller, this game will input the evidence of the seller as 1 or as 2, and the buyer is going to play left or right. And depending on whether you play left or right, you're going to get the good with some probability and face a transfer. To make things even simpler, let's suppose that whatever you play, you get the good, and what changes is whether you have to pay X or you get paid minus X. Now, put yourself, suppose the seller deviates to this mechanism. How are you going to play this game? Let's think about that. Suppose you are the buyer and you see this mechanism. What are you going to do? You can walk away, which will give you 0, or you want to decide whether you want to play left or right, and your choice will depend on what you think is the seller's type. So now we are going to describe your behavior as a function of your belief. If you think S1 is deviating, you're going to play right because you're going to get paid X. This is great because you're going to walk out with money. So if when you play right, the profit vector that results for the seller, it's minus X. S2 is happy. He gets more than 0. I'm assuming X is positive here. So when you play right, S2 is happy. Now suppose you think that the deviation is coming from S2. What are you going to do? Left or right? Left, because you get paid. Come on, I want more enthusiasm. You're making money here, please. You're going to play left. When you play left, S1 is happy. So when you think, so now you either play left or right, depending on who you think is more likely. So you either end up here or here, right? We are in trouble, right? Because either S1 or S2 is happy here. So it's a deviation. No, well, you can tell me, wait a second. Well, because if the off-path belief is that if you see this deviation and you put probability a half to S1 and a half to S2, and you mix left and right with equal probability, then you get 0. So this trivial example shows the delicate construction of what we were discussing. For every deviation, we have to find the right belief and the right play to establish that this is not a profitable deviation. And this is not to establish crazy things, even to show that this freaking 0, 0 is an equilibrium. I'm sorry for the language. You have to do this. Okay, so this example, so now you see that all of these mechanisms, all of these deviations, of course, left, right, you can have more messages, they will lead to profit vectors. And all of these profit vectors are feasible given beliefs. So now when I was talking about the Pareto frontier profit vectors, I'm talking about this red set here. So now you can also see the need to bound transfers. When the belief is 0, so S1 is impossible. Mu 0 means that the probability that the seller's type is 1. S1 is impossible. Type S1 can make a lot of money because the consumer thinks he never happens. So this is I can put this up to infinity, so we have to bound it. So for belief, for extreme belief 0, this gives you the boundary of the Pareto frontier of profit vectors. For belief 1, when you think that the seller type is S1, S2 can get a lot of money. So this is the Pareto frontier. The unique point that is on the frontier for interior beliefs is 0, 0. So this model I'm writing here, it's a private value model. This is one of the cases studied in Mask in Tirol 1990, and what this paper teaches us is that the Pareto frontier profit vector is equilibrium, and for any interior prior that's 0, 0, so we knew that actually from your paper, we shouldn't have been so worried. And and it's in, this example also illustrates that the Pareto frontier profit vector for private value cases coincides with the full information profit vector. Here the full information profit vector is obviously 0, 0. This is a general property. When you have private values, so when the consumer does not care about the seller's type, the Pareto frontier profit vector for the prior will coincide with the full information profit vector. And that teaches you also that Meyerson's optimal auction is where if you had if we had private information, is also the unique outcome for an informed seller, if the seller had private information. Okay, so now let's try to prove this 0, 0 is an equilibrium using a different technique than Mask and Tirole, which is game theoretic. And I know you're really worried about this result because it's a very important, I'm joking here, that 0, 0 is an equilibrium of this game. But you know, this proof method works for any environment where the seller can extract all the surplus. He always wants to assign the good and can extract all the surplus. So if you want to establish that full surplus extraction is an equilibrium, whenever full surplus extraction is possible, you can use this argument. And whenever actually you can achieve full surplus extraction, and you have to always assign the good, always. So whenever you are assigning always the good to extract all the surplus, you can define an artificial zero-sum game, because basically what the buyer pays is what the seller gets. And this is the artificial zero-sum game, so I'm writing just what the buyer pays, but this is what the seller gets. And let's phi be the value of the zero-sum game. The min-max theorem says that if the value of the mean, now you can think that this mu star corresponds to a strategy of the raw player, how the raw player is playing. So if phi is positive, then there exists a mu star such that the buyer rejects. And if phi, the value of the zero-sum game, is less or equal than 0, then there exists a mu star and an optimal reporting and participation strategy of the buyer such that the seller's interim profit is less than phi for every S. So it's not a profitable deviation. So basically, if the zero-sum game has positive value, which means extracts more than a full surplus, then there will be some belief such that the buyer will reject. And if it has less than 0, then there exists a belief that makes that not a profitable deviation. This method of proof is okay if you always want to assign the good, but it doesn't work always if you want to exclude some types, which is usually what you want to do. I hope it's kind of somewhat clear. So there is a game theoretic way to show that special cases are a full surplus extraction is an equilibrium outcome. So now to construct equilibria more generally, we're going to use some insights, deep insights developed in Mask and Tirole in 1990. And it's actually we were quite surprised that they were useful in this interdependent value environment. We didn't expect them to be useful, but they were.
Because of the certification.
Yes, they are useful because of the certification. So these techniques are useful in the private value environment because in the private value informed principal problem, the different types of principal they can always kind of basically benefit by collaborating, because they don't, the agent that could not care less about your type. So the fact that you have superior information vis-a-vis the agent can help you relax the incentive and participation constraint of the agents. So that means that different types of principal are not in a very big conflict in the private value case. I hope I'm saying it kind of correctly. Here, the conflict of mimicking each other is eradicated by certification. But still, some technical aspects are not so easy, because when you are thinking about existence, there are going to be some additional complications we have to think about, because we don't know which which prices, which incentive constraints are relevant and which participation are relevant. We're going to have zero prices and all of these things, but these are kind of asides. But this, exactly this, is useful here because we have certification, and that's why these tools are not used in the Mask-Interior 1992 paper that looks at common values, because when you have soft information, they are not useful in general. Maybe there are in some cases. Okay, so an allocation is Pareto optimal for some belief mu if there exists weights, so weights on different seller types, such that it maximizes this weighted sum of payoffs subject to interim incentive and participation constraint for the buyer. So that's a weak definition. So we need, for some belief, we need to find some weights. So if we take the weights to be equal to the prior, Pareto optimal is corresponds to the ex-ante profit maximizing allocation. And if we take the weight and the belief to be degenerate, either 0 or 1, it corresponds to the full information. So both of these profit vectors are Pareto optimal. So now we can think about the Pareto optimal profit vectors for given belief mu, and think about the union as we take all possible beliefs about the seller, and we call this VPO. This is all Pareto optimal profit vectors. We take the union. So the set of strong Pareto optimal interim profit vectors is denoted by VSPO, and it's the set of those Pareto optimal profit vectors such that there is no belief about the seller, and vector of profits in the Pareto optimal one, such that V strictly Pareto dominates. And and there is no interior belief, so for beliefs that could be extreme, we need strict domination. But for beliefs that are interior, we just need weak domination. So if something satisfies these constraints, is a strong Pareto optimal. So an easier way to see it, because this definition is not very intuitive, and it's actually not so easy to construct the set of strong Pareto optimal profit vectors. I mean, those who are in computer science, I'm sure they're going to be better than us, but it's not a very easy exercise. At least we found it not so easy. So this is the outer envelope. The strong Pareto optimal profit vectors is the outer envelope. So let me show you a picture to make this clear. So as I said, this is like they define these concepts for a private value setup. And as I said, for private value setup and linear, this is a singleton. For all interior beliefs, the Pareto frontier is a singleton, and it's equal to the full information outcome. So you see in this is a very striking way in which the case with linear transfers is very non-generic. And we use that all the time in mechanism design. Okay, so this is the illustration of this shaded area are Pareto optimal profit vectors for different beliefs. The strong Pareto optimal profit vector is this red set here. So again, for the extreme beliefs, we get this vertical and this horizontal line. And then for beliefs above 1/3, we get this point. For belief below 1/3, we get 5-1. And we get, for belief 1/3, we could have any point on this line. So this is basically the set. So that picture, if we have an analogous to the theorem of so what our theorem is going to say is that if we is that there's going to be a profit vector on this frontier for every prior. That's the first thing we have to show. And this vector of profit is going to be an equilibrium, and it's ex-ante optimal. So you see that there is a Pareto frontier profit vector for every prior here, because for every nu above a third, from 1/3 to 1 we get this. So we have, for 1 we have this, for 1/3 to 1, open 1 we have this 3, 2, for 1/3 to open from 0 to 1/3 we have this point. So there exists for every prior. And you see now why this for 1 is not an equilibrium, because it's not on this Pareto frontier. But I'm going to also show you why for 1 is an equilibrium in an easier way.
Sorry, can I ask you a stupid question?
Please, yes.
What is the? I don't understand the presence of these pairs that are. So the pairs on the vertical line, for instance, that are above 3, 3, 2, 4 to the right of 5, 1.
You don't understand those.
They're only relevant when they're degenerate beliefs.
Okay. But you can do the other pairs.
Basically, if
it doesn't
there's a
exist, you can
probability
give him anything you
0
want.
at type 1, the type 1 principal could get as high a payoff
Oh, I
as she
see.
wants within the...
If you don't believe they exist, you can pay infinite.
Right.
Exactly.
Okay, thank you.
Exactly, that's why, yes. Okay, so for every prior there exists a belief, there exists a strong Pareto optimal profit vector. So the idea of the proof is the same, but the details are a bit more involved, because in that paper, the agent's type is ranked. There's a good or a bad type, so you can anticipate that which incentive and participation constraint bind, and each principal type is thought as a trader of a fictitious exchange economy where they're trading slacks. So basically, we are cooperating to relax incentive and participation constraints, and we're able to kind of come into agreement by trading slacks of these constraints among ourselves. So here, we have no idea what constraints are binding, because we don't have better T's or lower T's, whatever. So there could be a lot of prices that could be 0, and Valor's law may fail in situations where you have a non-associated demands. So there is an example of that. So Milovanov and Traeger extend this insight of existence of masking Tirol in a richer situation where we cannot anticipate which constraints are binding, and they show that Valor's law may fail. And when Valor's laws fail, which Valor's law is basically people at the optimal demands, the budget constraint is satisfied with equality. When Valor's law may fail, Valor's and equilibrium allocations need not be Pareto optimal, and existence here is proven through existence of Valor's and equilibria. Okay, so here, so in particular, Milovanov and Traeger cannot use this solution concept because it doesn't exist necessarily. So here, we are able to have existence because of the fact that there are transfers which enter linearly. So Valor's law then is always satisfied. So that's a technical thing, is in the appendix if you're interested in those things. And there are some other conceptual differences, because now we have interdependent values. These are more technical things. Okay, so another thing that is that happens here and is not true in general is that every SPO for the prior is ex ante profit maximizing. I don't want to spend a lot of time on this because this is not a very deep proof. We use the linearity in transfers to establish this. So this is the important theorem. Every SPO for the prior is an expectational equilibrium of the mechanism proposal game. And combining this result with the previous one, we know that there exists an ex ante profit maximizing expectational equilibrium. In the example, it was a 3-2 vector. So before I do the proof, I want to show you something about why we knew that the unique equilibrium of the example why we knew that if that game had an equilibrium, we were not sure, it must have been 3-2. Okay, so let me do this first, because actually I'm going to use also this to show you, to explain something. So if something is an equilibrium of this initial example we started with, this 5, 3, 1, 2 thing, it must survive this deviation. So suppose the seller deviates to this mechanism where you play left or right, and you always get the good, and then you pay the same amount as the amount you value the good. So what do you play? If you face this mechanism, again, you can either reject play left or right. So now we are familiar with these games. You either play left or right depending on whether you think it's coming from S1 or S2. If you think it's coming from S1, you're going to play right. If you think it's coming from S2, you're going to play left. When are you indifferent between playing left and right? At the belief 1/3. So if I want to plot the payoff vectors of that mechanism as a function of the off-path belief, well, I know I get this orange line. I get that for belief above 1/3, I will get this point. For belief below 1/3, I will get this point. And then, of course, I know that if something is an equilibrium, it must be above the full information profit vector. So I get also this vertical and horizontal line. What is this set? This is the suppo set. So before knowing the general technique, we knew if something is an equilibrium, the only thing that could be an equilibrium must be 3, 2, because that's the only thing that is feasible and is not dominated by anything that I can achieve with this deviation. And notice that I described here everything you get as a function of every belief. So whatever the belief I have, I'm going to be here. I cannot be outside. So the only thing feasible for the priors is 3, 2. So that's the end of the story. I could imagine a million other deviations, but for what matter, I have only one chance here. And in this game, in this example, we were lucky because we actually are able to get the whole Pareto frontier with one deviation. So this is like a canonical deviation. We would have loved to have canonical deviations because actually we would have been able to show uniqueness in a very nice way, but there are no canonical deviations in general. So that's why the theorem, it says every SPO for the priors and expectational equilibrium, whereas if we had canonical deviations, it would say that only SPO for the prior is an equilibrium. And to get that, we cannot do that in general. We need extra assumptions. And assumptions that would give you that are discussed in Maskey and Tirol 1990. You have to introduce a fictitious player, which I don't have time to explain here. So let me spend a few minutes on the proof. So take a strong Pareto optimal allocation, P hat X hat, and we're going to be looking for strictly positive prior beliefs or interior beliefs. And as I said, this has a profit vector V hat, and we are going to along the path, all principal types will offer a mechanism that will map. Now we have assuming own type certifiability, as I said, so that where mu hat gets evidence from the seller and direct reports from the buyer and maps the probability of trade and transfers. And the mechanism is such that it's equal to this allocation if I'm getting evidence which I'm expecting, and it's 0, 0 otherwise. So it's trivial to see that this mechanism implements the SPOP hat X hat. Okay, that's fine. So that's how we can implement that. So the inscrutability principle is used here. Every principal type proposes the same thing. It's a simple thing, direct thing. That's fine, it implements, it's feasible. SPO are feasible by definition. We have the definition. So now we have to show that this is immune to deviations, to arbitrary mechanisms. So think about the seller deviating to a mechanism M, and think about Vm of mu, which is basically the convex hull of the set of continuation equilibrium profits of M when the belief is mu. And V of M without this argument is the convex hull of the union of those things. So why am I taking, so now I need to be thinking about all possible beliefs when I'm thinking about this deviation. So now, for every profit vector in this set, which are many profit vectors, and for every belief we are going to define a correspondence, which is going to take beliefs and profit vectors to itself, and it's going to actually, so the correspondence takes mu and V. So V is something that is feasible. So it's going to take, for every mu and V, it's going to map this to beliefs and profit vectors given mu. So the belief that is chosen is the one that maximizes the difference between V hat of S and the conjecture equilibrium profit vector. So this correspondence is analogous to the correspondence used in Maski and Tirol. So this correspondence has a fixed point by Kakutani's theorem. And what happens at the fixed point? At the fixed point, mu star maximizes. Mu star, maybe there's a typo, I don't know. Mu star is the argument that maximizes this difference. So what I'm doing here, I am doing a belief design exercise, but because what is the belief is going to do? The belief is going to, that I want to choose is the one that maximizes the difference between the deviation, the payoff of the resulting from deviating to mu, compared to what I'm thinking is an equilibrium. So now actually the belief I'm designing is going to assign positive weight, you're going to see, only to types that would have been benefit by proposing M. So it's a nice belief. So the belief is the one that maximizes this difference, and so the fixed point, mu star maximizes this, and V star is in the equilibrium set of is in Vm of mu star. So after any deviation, consider that belief for the buyer and the corresponding continuation equilibrium profit vector. So now think about the seller types who have V star of S bigger than the bigger than the SPO, and those who don't benefit basically. This set of types that benefit cannot be the whole set of types, otherwise this would not be strong Pareto optimal. So this set is non-empty. So now I am going to set probability 0 to all these types in J. And this part differs from the proof in Maski and Tirol. It's because we're not using here the property that this is valorizing equilibrium. We're just using Pareto optimal property. This is an aside for Eric, sorry. So it assigns 0 probability to those types who don't benefit. So take now V star is feasible given mu star. Mu star thinks these types in J are impossible. So what I'm going to do now is I'm going to take this profit vector and I'm going to construct a new one, V tilde, which is going to equal to V star for all types who liked the deviation, and I'm going to set it equal to V hat plus epsilon for those types that I think are impossible. This profit vector, it is feasible for mu star because these types are impossible, and actually this profit vector is better for every type than V hat, which contradicts the fact that V hat is a strong Pareto optimal. So I has to be non-empty. This is a contradiction. Has to be empty. Sorry, I'm sorry. Has to be empty. I has to be empty. So we cannot have, with these beliefs, when we choose the beliefs like this, we can make sure that this M is not a profitable deviation, and that's the end of the theorem. And if you add a dummy player, you can show this is uniqueness. And if you have partial certifiability and the SPO turns out to be feasible for this partial certifiability structure, then again, the result extends to partial certifiability, and that puts everything together. So you see the introduction of certifiability and allowing the seller to offer more general selling procedures yielded that unraveling is not an equilibrium, which is important in terms of economic substance, because unraveling has been used as a justification for you don't need transparency laws in some financial markets. Here, if you use more complicated contracts, like these evidence conditional contracts, you get other things. And that's all. Thank you for your attention. So I don't know if there are any questions, or I guess I'm over time. Sorry.